Okay, so we're going to finally start getting to a point where we can start doing some circuit analysis here and explain why we've gone to this complex power idea here. Now, just to kind of again review where we're at, we started off just by doing power is equal to current times voltage. And we got an ugly expression for that, and we did a lot of trig substitutions, but then we wound up with that the same equation here, is still voltage times current, was my average power plus my average power times cosine of 2 omega t plus my reactive power times the sine of 2 omega t. Not plus, it was a minus. And then, of course, we had my equations for average power, which was Im Vm over 2 cosine of theta v minus theta I, which, remember, there was other things we could write with that. I effective times V effective times a power factor. And you can kind of mix and match those. And then we also had that my reactive power was equal to Im Vm over 2 sine of theta v minus theta I, which again you could write as an effective voltage times an effective current times an effective voltage times a reactive factor. And then we had this weird thing that we called complex power, and we defined it as P plus JQ. Now, this is what we're going to look at today, is why are we doing that this is P plus JQ? Well, let's just see why we are going to possibly do this and how this could possibly help me compute power here. Because I want to be able to do this by looking at a circuit and compute these things. Alright, so if I define it like this, let's first remember, let's write this out here. This would be, I'm going to write this as Vm Im over 2. I'm going to expand it out here, cosine of theta v minus theta I plus j Vm Im over 2 sine of theta v minus theta I. Alright, now one thing we can clearly see here is I could factor out these Vm Ims over 2. So that's what we're going to do here. We're going to write this as S is equal to Vm Im over 2 and then I'm going to have this times cosine of theta v minus theta I plus j sine of theta v minus theta I. Okay, but now what I'm going to use is Euler's identity, and I'm going to write this as Vm Im over 2 E, and then I'd have it to the j theta v minus theta I. Well, I'll expand that out a bit and write this as E to the j theta v times e to the minus j theta I. But wait a minute here. That negative there is just a conjugate, is what that negative does for us. And so, if I think about this here, what I wind up getting here is that this would be equal to Vm Im conjugate. So this refers to conjugate over 2. So wait a minute, this is the big deal moment here. S is equal to Vm Im star over 2. These are phasors. I'm sorry, it shouldn't be Vm Im. I was like, and right here this shouldn't be either. This should just be capital V, capital I, because these are phasors. Because I could just say, well, this is Vm at an angle of theta V, this is Im at an angle of negative theta I, and so I basically get that my complex power is equal to voltage times current over 2. But it's complex current, not complex, the conjugate of the current, which we could rewrite here as S is equal to V effective times I effective conjugate. So again, I just want to emphasize this little star here means conjugate. Now this goes even further because we know all of our impedance studies here. We have that, you know, V effective is equal to Z times I effective. And so what we also get is two other equations, that my S is equal to, now this is different than what we're used to. It's the magnitude of the effective current squared times the impedance, which is the same thing as the magnitude of the effective voltage squared divided by the conjugate of the impedance. So these are two useful equations, and then the other useful equation is I effective times, I should write this, V effective times I effective squared. Not squared. Damn it. I effective conjugate. I'm losing my track of my thoughts here. So these three equations are important. Now you also have to remember, if you don't have effectives, to being able to convert them to the over 2, the V times I over 2. Okay, so we're ready to actually kind of go through an example here. So let's look at an example. And I think once we start doing some examples here, this concept of complex power is going to make a little bit more sense here. So let's just look at a very simple circuit. $250, oops, that shouldn't be a current there. That should be a voltage. 250 at an angle of 0 degrees, and then this is an RMS. Drawing my circuit. Okay, so for this problem, what we're going to do is, and this here, I should put this as my load here. So, given the above circuit, compute the complex power delivered to the load what is P, Q, PF, and RF. So I'm going to go ahead and find PQ, PF, and RF, but I'm going to do this first problem in a couple different ways here. So let's first here, I'm supposed to compute the complex power going through this load here. Well, if I just computed the current here, I could use one of my equations here to get the power through that. But if I compute my current here, I could easily compute the voltage across that load here. So that's the approach we're going to take this first time. Alright, so to compute the current, this is a simple series circuit, so we would just have 250 is equal to I times 1 plus J4 plus 39 plus J26, which means we have 250 is equal to I times 40 plus J30. And so we would get I is equal to 250 divided by 40 plus 30I. That should be actually a pretty nice number. Yeah, and it is. It's 4 minus J3 amps. And I'm going to go ahead and write RMS, because I always like to make sure that I write RMS down, because remember, we have two forms of the equation here for power, and I'll get to that in a second. So we want to also compute the voltage across the load, which would just simply be my current times my impedance. So the voltage would simply be 4 minus J3 times my load here is 39 plus J26. And if I do that, I get 234 minus J13 volts. Now, remember, power, and this is, I should make sure I've been saying that we should do this, RMS. Power is either equal to V effective times I effective, which is the same thing as complex power, I effective conjugate, or V times I conjugate over 2. So the question is, which are these that I have found here? Are they effective voltages, or are they non-effectives? And because they're RMS values, these are effective voltages and currents. So maybe we want to also get in the habit of just always writing down what kind of voltage you have, or current. So we've got effective voltages and current, so my complex power is simply going to be my voltage, which is 234 minus J13 times the conjugate of my current. So the conjugate of the current is 4 plus J3. And so if I do that computation, I get 975 plus J650 volt amps, which from this we can now see here, we can just pick off, this is P, my average power, and that's Q, my reactive power. So the only additional step we've had to do here is, we found voltage and current, but we have to make sure to use the conjugate of the current. I can't emphasize that enough, and I forget to write that down even sometimes. So let us see, though, another way we could get this power here, because we're still not done with the question here. But remember, we had that complex power was also equal to the effective voltage squared times my impedance. Well, let's see if we could do it that way and get the same answer for my power. So my effective current is equal to 4 minus J3, amps, and the impedance of my load was 39 plus J26 ohms. Alright, now I need to look at the magnitude of this. Actually, the easiest way to look at the magnitude is to convert to polar. Because if I convert that to polar, you get 5 at an angle of negative 36.9 degrees. But this right here, that 5, that's the magnitude of I effective. So if you convert to polar, you get the magnitude right away. So the magnitude is 5. Alright, so then this means, using all my equations here, that my power, my complex power, should be 5 squared times 39 plus J26. So let's see if we get then the same answer. And of course, I just did it on my calculator, and we shouldn't be surprised that we do get the same answer, which is 975 plus J650. And so we clearly have very easily P, and again this would be volt amps. P is 975 watts. Q is 650 var. Now it's also asked for the power factor and the reactive factor. How do we figure those out? Well, the way you figure those out is you simply draw a vector diagram here, is what I like to think of it as, and do some right triangle trig. So what we have here, well, and it's always important to make sure you keep track of the signs too, because that's going to make sure whether you have the power factor as positive or the reactive factor as positive or negative. Alright, so 975 watts, so that means I'd have 975 here watts, and then Q would be 650 here. So if I look at it, I have these guys here, and then this here is my S. And then this theta here, cosine of theta is going to be your power factor, and the sine of theta is going to be the reactive factor. So let's see what we get here. Well, I have 975 and 650, but wait, my S is 975 plus J650. Well, that's not a real nice number here to get this, but remember, well, what could we do? We could put this in polar format. And if we put this in polar format, we get I'm sorry, I can't write down what I have on my calculator here. 1172 at an angle of 32.69 degrees volt amp. Now, there's actually two ways you could go about doing this here. So you could do the cosine of theta, which would be the cosine of 32.69 degrees, but that's also equal to just simply adjacent over hypotenuse, 975 over 1172. But either one that you do, you should wind up with a power factor of 0.482. And then the sine of theta, which would be the sine of 32.69 degrees, or it would be opposite over hypotenuse, so 650 over 1172, and then that would give me a power factor well, if I typed in the right function here, I typed in cosine again, of 0.540 as my reactive factor. So this is my power factor, and this is my reactive factor. All right, so this is just our first example, and I kind of scrolling back up here just to kind of, I know this video has gone a little long, I'm sorry about that, but we just did basic circuit analysis to still compute my current, and then depending on which way you wanted to do it, you just have to remember, if you use this power equation, you have to do the conjugate of the current. So we got the current as 4 minus J3, but when we did our power computation, we did 4 plus J3. So we've got a first example done, and essentially the next several lessons are going to be just some more examples of how to compute power with circuit analysis.